All right, everyone, Mr. Graham here. Today I'm going to introduce you to the next topic, the next unit. It's going to be on electricity, essentially, electric forces, and then how those electric forces drive electric circuits. So what we're about to learn will actually date back to what they started figuring out in about the mid-1700s. One of my favorite scientists, Benjamin Franklin. We know him from government. We know him from the history of the United States. But he was also a first-rate scientist, very good scientist, and was influential in the framework, or in the development of the framework of electricity, the physics of electricity. In physics, one of the major branches of physics is electromagnetism. So electricity and magnetism, which we'll cover later, are intimately related, and you can't have one without the other. And we in fact use magnetic stuff in order to produce the electricity. So what we're going to learn about now is the fundamental underpinning of essentially how the modern world is powered. You know, where our lives are dominated by electricity. Without electricity, we'd still be hunter-gatherers. We'd still be hunting for food. We'd still be foraging in the forest. We wouldn't have the buildings. We wouldn't have machinery. We wouldn't have stuff like that. So it's very important, but it's also interesting to see how small-scale the development was before it became, the global phenomenon that electricity is. So the first thing we're going to talk about are electric forces. Electric forces essentially drive electric circuits, and so we'll talk about those electric forces. The thing about electric forces and electricity in general is that unless you got like a lightning bolt or a spark or a little shock, a little zap, like you get when you rub your feet on the carpet and then zap your little brother or sister, it's invisible. We can't see electrons. Electrons moving is essentially electricity, and so we can't see it, and so we have to measure these things indirectly. We have to figure this stuff out indirectly, and then expand on that to the development of circuits and stuff like that. So I like pointing out the first thing I like to show my students when introducing electric forces is an experiment you can do at home. All it requires is some Scotch tape. So here I got two pieces of Scotch tape that I've stuck together. Let me zoom in a little bit. Two pieces of Scotch tape that I've stuck together, and I'm going to rapidly pull them apart. And then as I bring them close to each other, you'll see that they get attracted to each other. You get an attractive force. That's actually an electric force responsible for that. Even if I turn them around, they're still going to attract, no matter which way. Okay? So notice that they were stuck together at first. Now if I stick them both on the table where they're not stuck together, and then I rip them both off of the table, an interesting result will happen. Instead of an attractive force, I now get a repelling force. Okay, so now I have a repelling electric force. So what's going on here? Well, it turns out the objects become what we say charged. And by charged, I mean positive or like negative charge. You've learned about that before. Positives attract, opposites attract, and the same charges repel. Two positive charges repel, two negative charges repel, and then a positive and a negative charge will attract. So whenever I charge the pieces of tape by sticking them together first, overall they're neutral, but when I rip them apart, one of them will actually take charges from the other one. It'll actually rip electrons from the other one because there's two differing surfaces. You got a sticky surface and a smooth surface. Anytime two surfaces come into contact, you can either rip them apart rapidly or rub them together. You typically get a transfer of electric charge. Sometimes it's not enough to be measurable, but sometimes it is. And so when we say we charge an object in order to experience the electric force, that's what we're talking about. Another experiment I really like, go get a produce bag. Hopefully you're eating your fruits and vegetables. Get a produce bag and cut it into a loop. I'm going to zoom out for this one. And then you probably don't have rabbits fur at home, but it turns out that rabbits fur is really good at doing this, really good at charging objects. It's rabbit's fur actually, when you make contact with an insulator like plastic and you rub it against it, you'll actually get a transfer of electrons from the plastic to the rabbit fur. And so the rabbit fur will take electrons, it's the opposite. The rabbit fur will lose electrons to the plastic. It'll become positively charged, and then the plastic will become negatively charged because it gains extra electrons. Same thing with balloons. If I rub this balloon with the rabbit fur, you can actually hear the static shocks you can hear the static electricity there. So this is now charged. This is now negatively charged because it gained electrons from the rabbit fur. And then I'm going to do the same thing to this loop of produce bag, and it will also gain electrons. So if both the balloon and the the piece of plastic gain electrons, then I should get two negatively charged objects repelling each other. And what's cool about this little experiment is you can actually get the loop of plastic to float due to the electric force. Ooh, there we go. Am I on the camera? Yeah. So the loop of plastic is now floating because there's a repelling electric force from the balloon to the plastic. Okay. So that's a fun little experiment you can do at home. If you don't have rabbit's fur, that's fine. It just rabbit's fur works really, really good. If you don't have rabbit's fur, wool works as well, just not quite as good. Okay. So that's how we charge objects. You just make contact and either rip them apart like with the tape, or you just rub them together like I did here. And that's why when you rub your feet on the carpet and you touch your little brother or sister and they get a little zap, is because of you've charged yourself and you've created an electric force. That electric force will then, if it's given a pathway, shoot a little bolt of electricity from one object to the other. Okay? So how do we quantify the electric force? Well, it's kind of strange, unless you understand that in physics, there's a lot of inverse square laws. You know, we've experienced the major one is the gravitational force. Gravitational force, according to Newton's law of universal gravitation, you can calculate the attractive force between two masses by multiplying the universal gravitational constant, big G, times the product of the two masses divided by the distance separating those two masses. That's Newton's law of universal gravitation for gravitational forces. It turns out that the electric force, and again, this was discovered in the 1700s, the electric force between two objects is equal to not the gravitational constant, obviously, but it's a constant that gets the symbol lowercase k, sometimes with a subscript c. Actually, let me put it, the way it's written on the formula sheet is this constant is out in front, times the product of not the two masses, but the two charges, Q1 times Q2 over the distance separating them squared. And if I was writing Newton's law of universal gravitation in a similar way, it would look like this. So when we're talking about electric forces, we're not talking about masses, we're talking about charges. And those charges we actually measure in a unit, just like we measure mass in kilograms, we measure charges in units called coulombs, named after a guy whose last name was Coulomb. And so this constant is also named after him. This is called Coulomb's constant. It's on your formula sheet. It's actually a much, much larger number than big G. Numerically, it's like a billion million times bigger. So the electric force is actually much stronger than the gravitational force. You don't need a lot of charge to have large electric forces. You need a whole lot of mass to have a large gravitational force. Okay. But notice that these two equations are essentially identical in the way that they're written. And that's kind of strange. Nature just works like that. Now, the major difference is that the gravitational force is always attractive. The electric force can either be attractive or repulsive. If I have two positive charges, they repel. If I have two negative charges, they repel. If I have a positive charge and a negative charge, they attract. And we've already seen that with this little tape demo. Okay. I can also see an electric force, and a lot of students like this. It's fun. You probably have seen one of these before. It's that thing that makes your hair stand up whenever you turn it on, the Van de Graaff generator. Named after a guy whose last name was Van de Graaff. That's as far as I can zoom out. So what I have attached, I'm going to attach this little guy. This little guy right here. It's called a pith ball. It's a little object that has a metal coating on it, so it'll actually get charge loaded onto it pretty quickly. And if I just put it right here and then turn the Van de Graaff generator on, the Van de Graaff generator is very simple. It has a belt that goes over a spool. And as the belt goes up and makes contact with the spool, and then it goes over, and then it breaks contact as it rolls over the spool, you get a transfer of charge just like with ripping the tape apart. And what happens is that the Van de Graaff generator dome ends up with a positive charge. And that positive charge will then pull electrons, because the electrons in the little ball are attracted to the Van de Graaff generator, pulls electrons off of the little ball, and then transfers them to essentially the base here. And so not only does the dome get positively charged, but the little ball gets positively charged as well. And so when I turn this guy on, it's going to be loud, sorry about that. It's now getting charged. There, now they're repelling. Now they're the same charge. So now the little pith ball and the Van de Graaff generator are at the same charge, and then I can use a ground wire to discharge the Van de Graaff generator, and immediately when I do that, the electric force goes away. Okay. So those are some demonstrations of electric forces. And maybe we'll mess around with the Van de Graaff generator. We used to mess around with the Van de Graaff generator quite a bit, but in today's world, or at least this year, because of physical contact rules, I don't know if we're going to be able to do that. Hopefully we will. All right. Now, when you charge an object, you get what's called an electric field. We're not going to go into electric fields too much in pre-AP physics or on-level physics, but if you want to take AP Physics C next year, that's a huge thing that we actually learn about in AP Physics C is electric fields and how to deal with them mathematically. But electric fields are also closely associated with something that we call electric potential difference, which is very closely related to electric potential energy. But electric potential, not electric potential difference, I'll talk about that in a second. Electric potential and electric potential energy are not exactly the same thing, but they're very closely related. And if you have an electric field, meaning you have a charged object, any charged object creates an electric field. If you have an electric field, you have electric potential. And if you have electric potential, then you have the capability of driving electric current. You might know of the common word used for electric potential, that's voltage. And so if you have a little D cell or AA or AAA battery, those are 1.5 volts. The little square batteries are 9 volts. If you play guitar, you might have a 100-watt amp head that uses much more voltage. If you plug into the wall, you're plugging into 120 volts. So you get an electric field when you have a charged object, and associated with that electric field, you have what's called an electric potential. Now I'm going to turn off the lights for this one. Because in order to have the flow of charge, you actually have to have an electric potential difference, meaning a difference in voltage. When you take your AA battery, the positive terminal is rated at 1.5 volts, but the negative terminal is always 0 volts. That's why if you take a wire and connect it to 2 positive terminals on the same type battery, you get no electric current through it. Nothing happens. If you put the battery in the wrong way in your device, it doesn't work. So you actually have to have the circuit go from the positive terminal on a battery to the negative because there's an electric potential difference. And there's a nice little experiment that I'll probably end up shocking myself with that will show this. Let me turn off both lights. I have what's called an emission tube here, a little tube, gas tube, filled with, this is actually neon gas, so you'll actually see the true color of neon. Neon gas, whenever you have electricity pass through certain types of gas, it excites the electrons. The electrons then de-excite and release light. That's how fluorescent light bulbs work. Any light bulb that doesn't use an actual filament uses the excitation of gas, electrons and gas atoms to produce the light. And the thing is that if I hold the bulb like this, let me describe what I'm going to do. I'm going to hold the bulb so that it's like this. And so the closest end to the Van de Graaff generator is at a higher electric potential or a higher voltage. The other end is going to be at a lower electric potential or a lower voltage, and I will get a flow of charge. Notice that it didn't happen when it happened mostly when it was pointing directly at it, and even happens way over here. It gives me a little zap. And but the thing is if I turn it this way, I don't get that same effect. If I hold it the same distance, get a little bit, but not really. I get shocked though. So the reason why it didn't flow when it was like that is because both terminals, both ends of the bulb were at the same electric potential, the same voltage, and so electricity did not flow. Must be a dry day. Van de Graaff generator works very well on dry days because humidity actually dissipates the charge that gets stored on the Van de Graaff generator. Oh, wrong way. Okay. So I've showed essentially you have a charged object, and in batteries become charged by essentially having chemical reactions go on inside of them that actually separate the charge, puts the positive charges on one end and the negative charges on the other. That's a pretty complex process. I don't really know much about it. Mr. Kelly up in the chemistry department, he definitely knows a lot about it. So if you have chemistry with Mr. Kelly. He can describe the chemical reactions that drive that process much better than I would be able to. So now here's the thing that gets real confusing, and I'm going to go ahead and bring up a diagram, or not diagram, a simulation, because there's a huge difficulty in studying electricity that is a relic of the past. Oh, I forgot to talk about my electric forces here. Here I just got a nice little simulation that has two charges, one positive, one negative. And when I hit play, they obviously get attracted to each other. Right? If I look at the forces, both objects by Newton's third law feel the same force. The larger object obviously accelerates at a lower rate, but they do get attracted. If I was to make this negative charge positive, if I was to flip the sign on these charges, then I get the exact opposite effect. I get now a repulsive force, right? The signs are still the same as drawn, but if I change it so they have the same charge, then they get repelled. So that's just a visual of something that usually is actually invisible and we can't see. Okay. All right. So the difficulty, though, for a lot of students, and again, this is a relic of the past. This is a relic of what happened when they were first learning this stuff back in the 17 and then developing it in the 1800s. They didn't know what electrons were. The early models of the atom, even the earliest models of the atom, hadn't been invented yet or hadn't been developed. And so we had no idea what made up atoms. We had no idea what these charges were. They just noticed that there's charge. There's this concept of charge. And you have two different types because sometimes you get attractive forces, sometimes you get repelling forces. But they didn't know what electrons were. They didn't know what protons were. And so Benjamin Franklin, we can actually blame him for this. He just arbitrarily said, okay, this one we're going to call positive, this one we're going to call negative. Sorry, I need a little coffee. So he just came up with that by convention. He just said, this kind of charge is positive, this kind of charge is negative. As we learned what the atom was, it was then discovered that, okay, what Ben Franklin called positive charges, we know now are carried in protons, and what Benjamin Franklin called negative charges, we now know are carried in electrons. So if I'm looking at a battery or a simple circuit that has a battery and two resistors, I'll talk about resistors in a minute, and I close this circuit and I start the flow, and I look at the electron flow. You can see that, right? Yeah. So again, these electrons are so small, you can't even imagine how small they are. We actually don't know if they even have physical size, because if they do, their size is much smaller than we are actually able to measure. But we know they exist. And electrons, as they move through circuits, they go from the negative terminal, because the negative terminal is the negatively charged terminal, and so they get accelerated this way. Okay. They didn't know that at the beginning. They didn't know which type of charge actually flowed whenever you had a lightning bolt or when you had a primitive circuit and you wired it up. They didn't know which direction the charge actually flowed. And so it was just assumed by convention, that's why it's called conventional current, that it was the positive charge that flowed. It turned out that was wrong, right? But Benjamin Franklin said, okay, these are the positives, they're the ones that move. I might be wrong, but if I'm wrong, it doesn't really matter because the math will still work out. Because a positive charge moving in one direction, as far as electricity goes, is identical to a negative charge moving the opposite direction. So what is called conventional current now assumes that the current flows from positive to negative. Again, this was discovered long after Benjamin Franklin actually made the convention for positive and negative charges, but we now know it's the opposite. The thing is that they never fixed it. And so if you become an electrical engineer, if you become a physicist, when you deal with circuits, you're dealing with the flow of positive charge, which is what we call conventional current. If you can't read it, it says conventional current. Here it says electrons there. What really happens in physical reality is the electrons move from negative to positive. But when you're an electrical engineer, when you're a physicist, you just say, all right, well, it's the positive charges, put charges in quotes because the protons don't flow. The electrons are allowed to flow. They go from positive to negative, okay? But the thing is, you don't have to revamp everything. You don't have to rework everything because it was over 100 years before the discovery of the naming of the positive and negative charges, and then the discovery that the electron is actually the negative one, and that's the one that moves. Over 100 years between those two, and so it's stuck. It's stuck. And so if you're an electrician or an electrical engineer, you assume that the current flows from positive to negative, where in fact it flows from negative to positive. The thing is that we didn't have to change anything because the flow of positive charge in one direction, as far as what it does electrically, is identical, literally identical to what happens when you have negative charge flow in the other direction. Okay. So keep that in mind. It is very confusing for a lot of students, understandably, but yeah. Okay. So that being said, let's actually I don't know why I turn off lights. Let's actually look at a demonstration of real circuits. So I've made here, and again, this is a lab that we use, some lab equipment that we usually use whenever we're allowed to do in-person labs. Here I got 2 batteries wired up with a switch, which when I close the switch, lights up this light bulb here. Okay. So again, the charge literally flows from the negative terminals through the bulb, through the switch, back to the positive terminals of the batteries. But in practice, we assume that the current actually goes in the opposite direction, from the positive to the negative terminals. Again, it doesn't really matter. And so when I close the switch, then the circuit is what we call closed, a closed circuit, and the electrons are allowed to flow. When I open the switch, the electrons aren't allowed to flow. Okay. Now you might have noticed this if you've ever played with circuits before, maybe snap circuits, those are kind of fun. If I put another bulb here and close the switch, the 2 bulbs are now much dimmer than the single one that was first. Okay. And then if I take another light bulb and wire them like this and then close the switch, now you can barely see them. You can see them, but they barely turn on. Okay. These light bulbs are wired in what we call series. So they are a series of light bulbs that are just wired in a straight line, right? Not straight line, but in one loop of a circuit. And each time you add another bulb, you actually get less brightness because that's the way it works. Okay. We'll develop the ideas there pretty soon. What I can do though is wire this in a different way. And if you ever sorry, I need some more wires. Back in the day when they used to make old school Christmas lights, cheap ones, they would actually wire them in series, and the problem with that is that if one light bulb goes out, oh, I didn't show that. Oh, dang it. Sorry, guys. Class is starting very soon. I need to get this done. If one of these bulbs goes out, it's like breaking the circuit. It's like turning the off switch, right? So here I got the 3 light bulbs on. You can see that they're lit up just a little bit, but then if I unscrew one of them, then all of them go off. So in old school Christmas lights that were wired in series like this, if one of them went out, they all went out. And to figure out which one went out, you'd have to go through the whole line of Christmas lights and then replace each one individually until you found the one that was the problem. How we can get around that is wiring light bulbs in what we call parallel. Now it's kind of hard to see, but this is light bulbs. This is a demonstration of light bulbs wired in parallel. So here I have my one light bulb that's lit up. Now I'm going to wire another light bulb in parallel. And you can kind of see I put 2 more wires here, and then I'm going to put the next light bulb in parallel to that first one, right? It'll literally be parallel, but it doesn't need to be. The wires can go in different directions. And when I do that, when I connect this other one, notice that the first one brightness doesn't change. It's the same. Maybe changes a little bit, but that's because of the increased resistance of the wires. And then if one of those goes out, the other one stays on. So if you're going to buy Christmas lights, well, nowadays they don't make them in series, but you would definitely want your Christmas lights in this way, because if one goes out, then it's really easy to see which one went out, because it's the only one that's not lit up. Okay, so that's basic circuits. Now it turns out that light bulbs act like what we call resistors, and lab resistors are big, and they're bulky, so we can actually see what's going on. But if you want to see real resistors that are used in actual circuit boards, I got a couple of them here. Again, if you've messed around with circuits, computer motherboards, things like that, you probably have seen things like this. So these are actual resistors. They got little colored bands on them. Come on, focus here. Focus here. Got little colored bands on them. Those colored bands actually tell you what the resistance is, the amount of resistance each one has. And resistors do exactly what their name implies. They resist electric current. So the bigger the resistance, the more it resists the flow of electricity. You might wonder why that would be important, why we would need increased resistance in a circuit. Well, let's say you have a circuit component, like something in your computer, that needs a required amount of voltage or a required amount of electric current, which is, again, the flow of electricity. That requires a certain amount of that. Well, you can control the amount of electric current by putting resistors into the circuit. And so that's what resistors are primarily used for. They're used for a lot of different things, but we only study basic circuits in this class. Actual circuits, like the circuits that wire up the building that we're in, or the circuitry in our computers, that's way over my head. I don't know what goes on in there. It's so complicated. But this is, again, the basics. The basics are voltage provided by the battery, electric current, which travels through the wires in a closed circuit, one that doesn't have an open switch. And then that electricity can go through a light bulb to light it up. That electricity can go through a resistor. When it goes through a resistor, it actually builds up a little bit of heat. When it goes through a blender at home, it gets the blender to spin. And so you're taking essentially the electric potential energy stored in the battery and then converting it to some other form. Anytime you turn on a light switch, you're allowing that electricity to flow through the light and turn that light bulb on. Okay. So one of the things that we do have to deal with in this class is how to understand how the voltage, the electric current, and the resistance of a circuit are related. And they're related by what we call Ohm's law. And it's a very basic law. It was determined by a guy named Ohm, and actually by another guy named Cavendish, who determined what the big G, the universal gravitational constant, was. But he also figured out Ohm's law before Ohm, but didn't publish his research, and so it's credited to Ohm. It was determined that the voltage that drives a circuit is proportional to the electric current that goes through the circuit, and that makes sense. The bigger the voltage, the more electric current you have. Now you got a little tiny battery, you get a little tiny electric current. You have a huge generator, you get a huge amount of electric current. It's also directly proportional to the amount of resistance within that circuit. So this is essentially Ohm's law. Now it only works at certain temperatures. If you get a light bulb that heats up a lot, then the resistance of the light bulb will actually change, and this equation won't be valid because if this changes as electric current is flowing through it, then this whole thing gets out of whack. But for a typical resistor over typical temperatures, this equation will hold. Okay. So that's a brief introduction to Ohm's law. We'll develop that obviously in the future. One thing I do want to point out is that if I have a circuit, so I'm going to draw my battery here, and then I have a wire that goes through a resistor, and so this will be my resistor. I'm going to draw my resistor here. And then goes back to the battery. If I add another resistor, and resistors you can think of light bulbs as operating like resistors. If I put another resistor there, and then I put another one here, then the battery doesn't see the three individual resistors, it just feels one total resistance. And so we call that total resistance the equivalent resistance. Okay. And for a series circuit, the equation that tells you what the equivalent resistance is that will then go into resistance here for the whole circuit is just the sum of the individual resistances. And the resistances are measured in a unit called ohms, again named after the guy named Ohm. Okay. This is the easy one to understand. You just add up all the resistors. For resistors in series, you add up their resistances to get the total equivalent resistance, and then you can plug that into Ohm's law for the whole circuit. What if though I have my resistors wired in parallel? So they look like this. So now I have my resistors here wired in parallel. Now it's a little more complicated. If you take AP Physics C next year again, we'll learn why these equations look the way they do. But to deal with the resistances here, and again I should have labeled these over there. This is R1, R2, R3. To determine what the equivalent resistance is for this circuit, we have to use this inverse proportional relationship, where 1 divided by the equivalent resistance equals 1 divided by R1 plus 1 divided by R2 plus 1 divided by R3. Okay, that's the equation that we use to figure out the equivalent resistance for this circuit. What you'll notice is that when resistors are wired in series, you get less total current, right? Because the equivalent resistance will be larger than any one of the resistors, so R goes up. Voltage is the same if you got the same battery, so the current must go down. So you get less current, less brightness in the bulb. That's why when I added bulbs in series, they got dimmer. Here, though, if you actually work this out and solve for equivalent resistance, you learn that the equivalent resistance for this circuit is always less than the smallest individual resistance for any of the individual resistors. So if this guy was 2 ohms, this guy was 10 ohms, this guy was 20 ohms, the equivalent resistance would be less than the 2 ohm smallest resistor. And so you get actual less resistance, and so you get more current. The battery's going to pump out more current in that case. Okay. So that's essentially a broad overview of everything we're going to be learning about in this unit. Again, I went kind of fast. School starts in 3 minutes, so I got to stop. But yeah, that's our introduction to electrical forces, voltage, current, resistance, and electrical circuits. And those little experiments I showed at the beginning of class, you can do those at home. They're fun to do with the tape. And I really like the balloon and the loop of plastic. Little kids really get a kick out of that. So yeah, give that a shot. All right. Have a good one, guys.